Hello everyone, I'm Wang Mengting from Southeast University, China. The topic of my academic presentation is high-Q surface acoustic wave humidity sensors based on tunable Fano resonance. My presentation is structured into four main parts as follows. First, I'll give a little background on Fano resonance. Fano resonance is widely used in biological sensors, reflectors, filters, and many other applications due to its unique asymmetry. The potential to enhance sensing performance by applying Fano resonance in resonance sensors is highly promising. The symmetric Lorentz line shape is often used to describe typical resonance phenomena. When a resonator with a narrow spectrum resonance couples with one that has a broad spectrum resonance, or in other words, the Lorentz resonance is superimposed with a flat continuous background, an asymmetric Fano resonance line shape emerges. A phenomenological parameter Q is defined to measure the degree of asymmetry of the Fano resonance. When Q approaches infinity or zero, the Fano profile reduces to a symmetric Lorentz line shape. The Fano resonance can be used to tune the bandwidth of the resonator and further increases the sensitivity and resolvability of the sensor. Next, I'll talk about the structured design of the soil humidity sensor. The surface acoustic wave device consists of the piezoelectric substrate and the interdigital transducer in the central area with Bragg mirrors placed on both sides. The humidity-sensitive material was electrospun on the soil resonator. The interaction of the sensitive material with ambient humidity induces mass changes that consequently influences the initial resonant frequency F0 and the sensitivity of humidity sensors. The soil resonator is characterized by the BVD model shown in this figure, where C0, Cm, Lm, and Rm represent the static capacitance, dynamic inductance, and mechanical loss, respectively. The admittance of sensor has a series resonant frequency Fs and a parallel resonant frequency point Fp. As mentioned above, Fano resonance results from the superposition of the Lorentz line shape of a discrete resonance with a flat continuous background. In the BVD model, the resonator is represented by a LCR series branch in parallel with a large capacitor C0. The admittance spectrum of the LCR series branch exhibits a typical symmetrical Lorentz line shape, while the parallel C0 branch behavior as a continuous flat background. The superposition of the two branches leads to the phenomenon of Fano resonance, implying that the soil devices inherently possess Fano resonance characteristics. In this work, we combine the Fano resonance and the soil sensor into the high-Q soil sensor through an external shunt capacitor. In the context of Fano resonance within soil devices, the pair of asymmetric peaks is directly related to the series and parallel resonance frequencies. As these two frequencies converge, the Q factor of the device increases within a certain range. The separation between the two resonant frequencies can be reduced by paralleling an external shunt capacitor CP. The optimized CP for achieving the maximum Q factor, which corresponding to the highest resolution, can be predicted through calculation. Then, I'm going to discuss some experiment details. The soil humidity sensor was tested with various shunt capacitors. The experimental results indicate that the maximum Q factor of the sensor is achieved with Cp equals 39 picofarad at 25 degrees and 20% relative humidity. The static performance of the sensor was examined using the test system as shown in this figure. The test humidity ranged from 30% relative humidity to 90% relative humidity. Both the adsorption and desorption processes were examined as a complete set of the experiments, and the sensitivity was calculated based on these test results. As shown in this figure, the performance of the source sensor with shunt capacitors is significantly better than that of the one without shunt capacitors during the static characterization test. By analyzing experimental results thoroughly, it can be concluded that without the shunt capacitor, the sensitivity of the sensor is 0.358 kilohertz per percent relative humidity. With an optimized shunt capacitor, the sensitivity increases to 0.417 kilohertz per percent relative humidity. A Cp of 39 picofarad consistently outperforms other cases, especially at 30% relative humidity, where the Q factor increases from 1,118 to 4,897. Despite the deterioration of the Q factor with increasing humidity, the shunt capacitor effectively counteracts this decline, resulting in better overall performance. Before I wrap up, I'd like to summarize my major work. In this work, a high Q factor soil humidity sensor that leverages the principle of Fano resonance is proposed. By the capacitive shunt technology, the humidity sensor is able to address the admittance and S-parameter spectrum, thereby increasing the Q factor and resolution of the sensor. This straightforward and practical design greatly enhances the Q factor and shows promises for future applications. That's all I show. Thanks for listening.